So let's have a look at part 2 of our AC current section. And what we're going to do is look at how do we go from AC, how do we get a flow of current that looks like this, to look like one that looks like this, a DC current. Now, we could just produce it like this at the power station, but we've already looked at why AC has so many advantages. It reduces power losses through transmission, and your generator is actually quite straightforward. So let's have a look at 2 stages. The first stage is a diode, a use of diodes for rectification, and the second stage is the use of capacitors. Now, the first way to get a nice flat trace is probably to get rid of the entire negative section of the AC trace, like this. Okay, so we're going to look at the first step in rectification, which is to go from here to here by chopping off the bottom end of the AC curve. So our first step is something called half wave rectification, because what we're going to do is we're going to take the AC wave and we're going to get rid of half the wave to make it look like this. And we do that with a component that we will put in the circuit called a diode. Now, diodes are semiconducting components that allow current to go through in one direction only. This is the symbol for a diode. The flow of the current in one direction is allowed to go through that component there. However, when it reverses, the diode does not let the current go through, and that's indicated by this little flat bit here. So you would draw the flat bit on your component to indicate a wall, like stopping the current. So as the current flows in an AC circuit, the current, when it's positive, depending on how you've got the diode wired up, but generally when it's in the positive direction, the current can flow. So this half of the curve is untouched, and when the current is negative, this half of the current is blocked. It's not allowed to flow. So we end up with something called half wave rectification. We no longer have the negative side of our AC curve. Now, what we're going to aim for now is something called full wave rectification. So how do we get, instead of losing half the wave, which is half the energy basically, what we're going to try and do is we're going to try and get it to flip up to the positive. So we'll try and get the negative side of the curve to register and flip up. And what we've got here is a diode bridge circuit. It's an excellent little arrangement and very clever too. Now let's have a look at how it works. Now let's consider when the current is positive. Here in this section A, the current is flowing this way, and it can flow through this diode quite happily and then continue through to the resistor. And then it will go up to E, flow to F, and then continue this way. And your circuit will be allowed to function perfectly. Now let's have a look at when we have a negative trace. Now when the current is flowing in the opposite direction, this way, it can no longer go flowing through the same diodes it did before, because the path is blocked. As you can see, the 2 diodes that it used before no longer allow the current to flow. So luckily there's another 2 diodes, F to B, which will allow the current flowing through here, and then E to A. Okay, so you will end up with a continuous flow of current. It's very clever. So when we have a positive flow, these two diodes are used, and when we have a negative flow, we use the other two diodes. There is always a continuous flow of charge, but this time in the positive direction. So what the full wave rectification circuit does is it converts the negative AC traces to a positive. It creates a wave in one direction only. Now if you go to the website, there is a really nice little simulation experiment that you can do just to play around with this kind of circuit. So how far are we in our rectification? We've gone from this to this. It's not quite DC yet because we want something like that. Okay, so we've still got one stage to go. We need to smooth out the lines, try and make them go as straight as possible. So that's what our capacitor is for, and that's our next little component. Now a capacitor is another component that you would put in a circuit. This is the symbol, two parallel plates, and that's pretty much what they are. The ability of an object to store electric charge is described as capacitance. An electrical component that is designed to store electric potential energy is called a capacitor. And the simplest kind of capacitor is simply two parallel plates with an insulator inside it. And that's what a capacitor kind of does. It literally just stops the circuit because it is a gap. It's a gap in the circuit. It breaks the circuit. But because it has these two wide plates in it, before the circuit stops, the charge accumulates on the plate. Now you think, why would I want to put a component in a circuit that's going to break the circuit? Well, it will break the circuit until you make the capacitor the source of the charge. So it's almost like it's a replacement for the battery. Here in this circuit we have a capacitor charging up. The battery is on, the capacitor stores charge, and as soon as the plates are full and can't store any more charge, it stops flowing. So what you do then is you open up the circuit and you make the capacitor the source of energy. As soon as you open up that circuit and get rid of the battery, then what happens is that the charge flows back. So you get like a little surge of current flow. So it's like a temporary store of charge. Now the capacitance is basically a measure of how much charge it can store on those plates. And it's a ratio. It's a ratio of the charge on the plates, Q, over the potential difference between the plates. So it's the ratio Q over V. And we measure this capacitance in farads. So 1 farad is 1 coulomb per volt. Let's have a look at the capacitor in a little bit more detail. For a capacitor, we have two conducting plates, and inside an insulating material called a dielectric. So we said this cannot be a material that conducts. It's a material that insulates and stops the flow of charge. Now, as you switch your battery on, your negative charge, let's assume electron flow rather than conventional current, the electron flow begins, and the electrons that cannot go anywhere else accumulate on the plate. So this plate becomes very negatively charged. Your positive charges accumulate on the bottom plate. Now eventually these charges become such that they stop the flow. Now if you think about these negative charges, because negatives are flowing in this direction, eventually this plate will be so full it repels them. So the charges stop moving and current stops flowing. Now when it's convenient, all those two plates can discharge, allowing a flow of electric current whenever it is appropriate for use. Another way of defining when that current stops flowing is when the potential difference across the capacitor equals the supply potential difference, the current stops flowing. So when your charge is accumulated here, and it creates or generates, a potential difference which is equal to the potential difference of the battery, equal and opposite, of course, then that's when current flow stops. Now this is really handy for mathematical questions, because if you have a 6-volt battery charging this capacitor, when the capacitor has charged, its voltage or the potential difference it will have available will also be 6 volts. So that's an interesting thing to bear in mind later for numerical questions. Yes, they are looming. But let's get back to AC. So we're almost here. Let's have a look at how capacitors can straighten out our AC rectified curve. So here we have a parallel circuit. We're getting an AC trace from the rectifier that looks like this. Half of it's going here and half of it's going here. We're going to worry about what we get in the voltage out. So what does the trace that we get from voltage out look like? Well, once the first peak arrives, the capacitor will be charged. So here we're getting a trace which goes up, it's a peak, but at the same time some of that current is charging up the capacitor. Now as the curve starts to come down, the current through the capacitor decreases. So the capacitor discharges, and what it does is it releases some of that charge through the resistor. It's kind of compensating for the drop in the AC. So instead of just getting a drop here, we're getting a little bit of current flowing from the capacitor. Once the current goes up again, the capacitor will charge again. So we end up with not a fully straight line, but we get the dips in our current flow here. These dips are compensated by the charge that's accumulated in the capacitor. I hope that makes sense. Okay, so I have a go at some of these questions. 53 you can't do because I didn't include the diagram, which was really clever. I'll try and get that ready for next time. And that's today's lesson. A quick and short and sweet one. There's only one left, which is on capacitors, and that one should be up tomorrow.